All right, let's talk about scaling transformations and similar figures. Okay, this section covers transformations that either enlarge or shrink an object from a point P. Such transformations are called size transformations or scaling transformations. The point the point P is called the center of the size transformation. The multiplier used to enlarge or shrink the object is called the scale factor K. The calculations used to make the transformation depend on the distances from point P to the vertices of the object. These distances are multiplied by K. So to enlarge or shrink the object, find the distance from point P to a vertex A of the object. Multiply this distance by K to get K times PA, where PA represents the distance from point P to point A. So PA would be the line segment. Then measure this new distance, K times PA, from point P in the direction of vertex A. This distance gives the new location of vertex A after the object has been size transformed. Then repeat this for all of the vertices of the object. Okay, so let's look at this example here. Okay, so we want to enlarge this by a factor of 2. So what we're going to do is we're going to take the distance from P to A, right? So we'll take this distance from P to A and this distance from P to B. We're going to multiply this distance by 2, right? So this is 3 units here and 3 units here. So that means we're going to double it to 6 units. So B prime is going to go out to here, okay? And then A prime is going to go out to here. And so then the enlarged triangle would look something like that, which we have down here, okay? So now it's been scaled. Okay, it's that easy. So step 1, measure the distances from P to each of the vertex of the triangle. One vertex of the triangle is on point P, so that vertex will remain at point P, right? Okay, since we're enlarging it from that point. The distance from point P to vertex A is 3 units, and the distance from point P to vertex B is also 3 units. Okay, so then step 2 is we're going to multiply each one of those distances by the factor 2. So K in this case, K is equal to 2. And so when we do that, we get 6 units for each of them. So now we draw out those new distances to B prime and A prime. So step 3 is we're going to measure 6 units from point P in the direction of vertex A, and then also we're going to measure 6 units from point P in the direction of vertex B to get the new locations of A prime and B prime. Okay, and hence we get the triangle, the enlarged triangle here. Okay, now let's do another one where now we're going to enlarge something like this diamond, right? So what do? Right, so here's point P, so this is where the center is that we're going to enlarge from, right? And so we're going to scale the 4-sided diamond figure by a factor of 2 using P as the center. So here's P. P is not on the figure. So here's what we're going to do. We're going to measure from point P to all 4 of the vertices A, B, C, and D. Okay? And then what we're going to do is we're going to double those distances. Okay, so we're going to multiply each one of the line segments, PA, PB, PC, and PD by 2. Okay, and then what we're going to do is in the direction of each one of these arrows, in the same direction as each one of these arrows here, let me just circle the arrows here. And so we got this one, and then we got this one, right? So now, once we measure those distances, we're going to now double them in the direction of the arrows to get these points. Okay, and once we get those points, then all we have to do is connect the new figure, the enlarged figure in this case, with an edge, a straight edge. Okay, but again, we're just following the same 3 steps. Now, what about shrinking? Same idea. So the only difference is when we're enlarging, our factor k is bigger than 1. When we're shrinking, factor k is less than 1. Okay, so in this case here, we're going to take each of the distances from P. So in this case, P is in the center of the trapezoid. Okay, so we're going to measure the distance from P to B. So PB, PC, PD, and PA. And what we're going to do is we're going to take those distances and we're going to divide by 2. We're going to cut them in half. Okay, and then once we do that, then we're going to plot the new distances to the new vertices, B prime, C prime, A prime, and D prime, and then connect those with edges. And so this is what we do here, and we get the new shrunken version of the trapezoid. Okay, so that's what we're doing. We're doing the same 3 steps, but now the result is that we get a smaller, scaled down version of the shape, in this case a trapezoid. Okay. Now, shapes that have been transformed by a scaling transformation, either enlarging or shrinking, are similar figures in to the original shape. Now, what does similarity mean? Well, it means that that there's a proportionality. The angles stay the same, right? They don't change, but the lengths of the sides do change, but they are proportional to the original sides. Okay, so let's talk about similarity now. Okay, so 2 figures are similar if and only if there exists a combination of an isometry, which is a rigid motion, and a size transformation that generates one figure as the image of the other. Okay, so here's the definition. Figures that are the same shape but not necessarily the same size are called similar. So this is different than congruent. Congruence means that they are the same size and the same shape. So that means that they have the same angles, same angle measure, and the same side measures. Okay? Similarity requires that they only have the same shape, but not necessarily the same size. So they're similar. The corresponding angles must be equal, and the corresponding sides must be proportional, like I was saying before. So let's look at an example here. Okay, so in this example, we have 2 rectangles. Okay, now, they have obviously the same angles, right? They're all 90-degree angles, right? But are they similar figures? In order to do that, we want to show that the sides, corresponding sides, are proportional. So we want to say that the proportion, right? The proportion of A to B, these 2 sides, is equal to the proportion of these 2 sides. So we want to set up a proportion like this. If it's true that A divided by B is equal to C divided by D, then they are similar figures. Okay? So suppose the two rectangles are similar and are related by the scaling factor k. We want to investigate how the perimeters and areas of the rectangles are related in that case. Okay, so we know that the sides of the rectangle are related to each other by this because they're constant, right? So that means C has to equal some multiple of A, and D has to equal some multiple of B. Right? Because if they're equal, then we should be able to get we should be able to go from one fraction to the other fraction by some multiple. Okay, so now let's look at the perimeter of the smaller triangle. Let's P be that perimeter. So P will be the perimeter of the blue triangle, and P prime will be the perimeter of the red triangle, the larger triangle. So we know that the definition of perimeter is going to be the addition of all four sides. So in this case here, it'll be 2 times C plus 2 times B for P prime. Okay, and then P likewise will be 2A plus 2B. Okay, which we have down here. Now, using this formula for P prime, we know that C is going to be K times A and D is equal to K times B, so we can substitute and we get P prime is equal to this, which then can simplify to this, right? By using properties of numbers, right? Using the distributive property. So we can factor out the K and we get this. And likewise, we get P is equal to this. And so if we put these two together, P prime and P, we see that P prime is equal to K times the perimeter. So the perimeter of P prime, the larger rectangle, is just going to be a multiple of the perimeter of the smaller rectangle. Okay, thus scaling a rectangle by a factor of K increases the perimeter by also a factor of K. So not bad. Now let's look at area. Let's do the same thing for area, see what we get for area. Now, if we let area A equal the area of the smaller triangle and A prime be the area of the larger triangle, and then of course we use the definition of area, length times width. So area of A is A times B, and area of A prime, right? The larger triangle is, or the larger rectangle is C times D. Okay, but again, if we use substitution, we know that C is equal to K times A, and D is equal to K times B. Then what do we get? We get A prime, the area of the larger triangle, is equal to K squared times AB, which is also the area of A, right? And so we get this. So by scaling scaling a rectangle up by a factor of K increases the area by a factor of K squared. So now these relationships between perimeters and areas will hold for any closed geometric figure that encloses a region of the plane. In other words, for examples, we have polygons, circles, ovals, triangles, rectangles, diamonds, trapezoids, whatever. Okay, so now we're going to summarize these results below. So here's what we have. So here's the theorem. Suppose that figures f and f prime are two similar figures where f prime is obtained from f by a scaling transformation with scale factor k. Then, if p represents the perimeter of f and p prime represents the perimeter of f prime, then the perimeters are related by p prime is equal to k times p. Also, if a represents the area of f and a prime represents the area of f prime, then the two areas are related by the formula a prime is equal to k squared times a. So that is true for all closed geometric figures. Okay, so now let's look at the areas of and perimeters of the two similar triangles. So let's say we have these two triangles. They're both equilateral triangles with a side length of the corresponding side length of 4 for the smaller triangle, 16 for the larger triangle. So we can see very easily that the scaling factor, in this case k, is equal to 4, right? Okay, so that means the perimeter of the larger triangle, right? So the perimeter P prime of the larger triangle is equal to, as we saw before, k times the perimeter of the smaller triangle, right? Okay, now if we, and again, by the way, we're assuming that we're enlarging, but what if the larger triangle was the original triangle and we were going to the smaller triangle? Then it would be a k. So k depends on where we're going. Are we enlarging or are we going small? Because if we're enlarging the triangles, then k would be 4 in this case. But what if we're going smaller? What if the blue triangle is the original triangle? Then k in that case would be 1/4. Okay, so it depends on the context as well. So keep that in mind. So, but in this case, we're assuming enlarging, right? So in this case, k is 4. So if we wanted the perimeter of the larger triangle, all we have to do is take the perimeter of the smaller triangle, which is 12, and multiply by k, which is 4. Okay, and so in that case, the perimeter of the larger triangle would be 4 times 12, which is 48. Okay, and the area of the larger triangle, we'll call that a prime, by the theorem is equal to k squared times a, the area of the original triangle. Okay, so the area of the original triangle, so the area here, in this case, of the equilateral triangle in this case, again, we can talk about how to find the area of the equilateral triangle here, because again, we can find that using trigonometry, again, using the height of the triangle, right? So we have, and again, 60-degree angle. So we can figure that out. And so we know that the area, we can figure out the area of the smaller triangle is 6.9 square millimeters. In this case, we're dealing with millimeters. And so if we take 4, right, k is 4, so it's going to be 16 times 6.9, so we get 104.10 square millimeters. Okay, and all we used to find the answers was using the theorem for the two formulas, the relationships for perimeter and the relationship for area. Okay. All right. So now let's talk about nomens. Okay, so now we're introducing a new definition. You may or may not be familiar. It's called a nomen. So a nomen is a shape which, when added to a shape A, yields another shape A prime. That is similar to the original shape A. Okay? Alternately, a nomen is a shape which, when subtracted from a shape A prime, yields another shape A, which is similar to the original shape A prime. Now, that's a lot to say, but it makes sense when you see the picture. So let's look at this example here, and it'll make perfect sense. So here we have shape A, right? And now we're going to add this shape here, right? And when we add this red shape to shape A, well, look what we get. We get another shape that is similar to shape A, and we'll call it A prime. Excuse me. Okay. So in this case here, this red shape is what we're going to call nomen A prime. Okay. Well, okay, actually, okay, they're going to call this A prime, not this. Okay, so never mind. Let me take that out. Okay, because they're going to call this, I guess they're going to call this shape A prime. Okay, but when you put A prime and A together, you get another rectangle that is similar in shape, okay, to rectangle A. Now, from the diagram, it appears that the L shape could be a nomen for the blue rectangle. Now, one obvious requirement is that the dimensions of the inside of the L shape must match the height and width of the blue rectangle. That's obvious, right? Okay. Since then, attaching the L shape to the blue rectangle forms a new larger rectangle, right? So that's obvious. In order for A prime to be a nomen to A, the blue triangle must also be similar to the combined blue and red rectangle. And that means the corresponding side lengths must be proportional. So we align the lengths as shown. So in other words, this length here and this length here has to match the corresponding lengths of the blue rectangle. But this length here and this length here on the nomen must be proportional to the corresponding lengths of the blue rectangle. That's what we're saying. So in other words, B plus Y must be proportional, must be proportional to B, and A plus X must be proportional to A, or what I'm sorry, let me say this again. B plus Y divided by A plus X is proportional to B divided by A. That's what I meant to say. Okay. So in other words, this is what we're looking at right here. Okay. That has to be true, right? Just by using the definition of similarity. Corresponding sides must be proportional. Okay. Now, there's another way to have a nomen for a rectangle. Given a rectangle, we can attach another rectangle to the longer side. So here we have the original rectangle. We can add this rectangle here, so this would be a nomen, and so we get a larger rectangle. Okay? And so the nomen would be, this would be a nomen if we, one, end up with another rectangle when we attach it, and two, the corresponding sides of the new rectangle are proportional to the sides of the original rectangle. Okay, so in other words, 3 plus x um, 3 plus x over 9 has to equal 3 over 9, right? Or the reciprocal. Okay. So we're going to set that up. So in order this to be a nomen, okay, let's show that this is, one, it is a rectangle. We can see that. The corresponding, it gives us a larger rectangle, okay? But let's see if it is proportional, if the sides are proportional. So what they did was they set up the proportion 3/9, right? 3 over 9 is equal to 3 plus x over 9. Or excuse me, hold on. 3 over 9 I don't know if this is right. Hold on a second. Oh, I see what they did. So here, they attach it to this end here, but this length here is longer, right, than this side. That's what they're. So even though they're attaching to this side, we want to correspond the longer side to the longer side of the smaller triangle. So that's where I made my mistake. So 3 over 9, if we do this side over this side, then we're going to do the longer side of the larger rectangle, which is 3 plus y, over, which is the longer side. So it's going to be the short side over the longer side. So if we're doing 3 over 9, then we're going to do what? 9 over 3 plus x. So that's how we set up this up. So be careful, because it's easy to think, oh, I'm just going to do this side here, like what I did, x plus 3 over 9 is equal to 3 over 9. That would be wrong, because I was mismatching the corresponding sides. Okay, so now that we've got that straightened out, this is where we have. Now we cross multiply, we set up this equation here. Now we just have to simplify using properties of solving for equations, right? So we use the distributive property to get this, and then we subtract 9 from both sides to get this. Then we divide both sides by 3 to get this, and we find that x equals 24. And so if x equals 24, so now we have what? As long as x is equal to 24, right? If they're similar, then that means x is equal to 24. And so we get a side length of 27, right? And so thus, if x equals 24, then the red larger rectangle is a nomen to the smaller rectangle, and the nomen red rectangle has width of 9 and a length of 24. All right, not bad. Okay, so let's look at this one. Triangular gnomon. Well, if we look at this, again, we have this triangle here, this blue triangle. Okay, now, again, if this is a gnomon, if this red triangle that we're adding to the rectangle is a gnomon, then the resulting triangle, which is the larger blue and red triangle, has to be similar to the smaller blue triangle, which means corresponding sides must be proportional. This is what I mean. We have this red triangle here. Okay, that's what we want. That's our gnomon. That's what we are suspecting that that's a gnomon. We want to prove that that's a gnomon. The original blue triangle is the triangle we're starting with, and that has a hypotenuse of 15 and then two legs of 12 and 9 with a right angle here. Now when we put this red triangle and combine it with the blue triangle, we get the larger triangle. The resulting triangle okay, now the bigger red and blue triangle is the one that we want to compare with the smaller blue triangle. So we know that if we're corresponding sides, that means the hypotenuse of the blue triangle, 15, corresponds to the here's the right triangle or the right angle here for the big triangle. So 15 will correspond to the hypotenuse of the larger triangle, which is y plus 9. So 15, okay? Okay, is that, so, well, let's hold off on that. Okay, also, 9, the shorter side, the shorter leg, 9, corresponds to 15, or excuse me, no, not 15. Yeah, the shorter side of the blue triangle corresponds to 15, which is the short side of the larger triangle. And then X, or 12, the larger leg, 12, of the smaller blue triangle corresponds to X of the big triangle. So now when knowing this, when we want corresponding sides, okay, if we want to correspond X, we're going to take the smaller triangle, which is going to be the two legs, right? The short leg. Let's look at the blue triangle. Let's take two corresponding sides of the blue triangle. Let's take 9 and 12, okay? The two legs of the blue triangle. So if we take 9 over 12, we take that ratio. Okay, we want to make sure that we have a corresponding ratio of the big triangle. Okay, so 9 goes with 12. That means on the big triangle, the smaller leg, which is 15, goes with X. So that's where we go 15 over X. Okay, and so now when we solve this, we get X equals 20. Okay, now we're not done yet. So that's one condition. Now we got to set up another proportion to solve for y. So y, now again, y, it corresponds to the hypotenuse of the big triangle. But y, we're ignoring the red triangle, right? We're looking at the big combined triangle. So in this case here, we want to take y plus 9, and we want to take the ratio of that with something else on the big triangle. And we don't want to use x because we don't want x involved because, I mean, we could now that we know what x is, but let's not. Let's use 15, which is the short side. Okay, so let's do 15. Okay, so now we got the hypotenuse divided by the short leg. So now let's look at the blue triangle. Now let's do the same corresponding sides. So on the blue triangle, it's going to be the hypotenuse, which is 15, divided by the short leg of the blue triangle, which is 9. Okay, now we got our proportions set up. Now notice how they have theirs set up a little bit differently. It's just flipped, okay? But it doesn't matter. It'll get the same results. So if you solve for y, you get 16. Oops. Okay, now what does that mean? It means that in order for this red triangle be considered a gnomon, then x has to be equal to 20 and y has to be equal to 16. Okay, that has to be true. Okay, if that's not the case, then the red triangle cannot be a gnomon. Okay, so now we have a way of testing to see whether a given shape is a gnomon. All right, let's end there.